Hi everyone, welcome back to my channel or welcome to my channel. Today I'm going to talk about a topic, as you can see here, time domain reflectometer, which is actually the name of an equipment. But anyway, the concept behind it, which is time domain reflection, is a very important topic because it comes up a lot when you're designing high-speed PCBs, or maybe you're in field and you're trying to find fault in a cable or something else. So this topic comes in handy when you're trying to find fault. Or, as I said, when you're designing high-speed PCBs, you have to be familiar with this topic or this concept so that you can understand what is going good or well with your design or what is going bad with your design. Okay, so without further ado, let's dig in. Let's see what is a time domain reflection coefficient or reflector, or the tool that measures that. Okay, so I don't know if you're familiar with reflection coefficient at all or not, so I'm going to start a little bit before and try to explain the concept of reflection coefficient, and then we go to this time domain version. Okay, so why do we care about reflections? Okay, why they happen and where they happen actually. Okay, so when most of the time when you're looking at cables, like a coaxial cable that connects to your TV, or maybe like a trace on a PCB, okay? In high-speed designs, or as I said, for regular cabling that transfer data to your devices, basically you're looking into a transmission line, okay? Transmission line, if you don't know about the topic, okay, go read about it a little bit. But right now in our lives, it's basically everywhere. And it's basically composed of two conductors, one of them carrying the current, one of them is carrying the return path of that current, or let's say it's the ground, okay? So it's composed of two conductors, and they both need to be there, and they are separated usually with a dielectric. So for example, here, this is the conductor that looks like a trace, or basically it's a metallic trace rectangle with a certain thickness. And then this is the return path of it, or the ground for this. So this is conductor number 1, and then this is conductor number 2. And they are separated with a dielectric slab, which is something that basically is non-conductive, okay? Now, when you're thinking about current going through this structure, okay, the important part is that most of the time we are thinking about current, we are like, oh, electrons are moving from this point to this point, right? Now, let's say in higher frequency, beside the current that is carrying the power, the DC power, you have another concept that is happening. That is the electromagnetic propagation, that is transferring your signal from one end to another one, right? Now, if there is no termination, let's say, between these two, okay, just like a coaxial line, for example, you just go from coaxial line from here to here, which you have an inner circular, like a cylindrical cable going in, and then an outer one, right? Those are the two conductors you have. Let's say you don't have a termination there. Does the signal go, like, travel through it? Yes, it does. How does that happen? It's just that in electromagnetic or in higher frequency, beside the conduction current that we are familiar with, where electrons move from one side to another, we have another concept, which is the displacement current. That displacement current basically is when in higher frequency, or in basically whenever you have a frequency other than 0, and the voltage changes from between these 2 points, then you have the electric field changing between them, and it's as if you have current going from here to here. Okay, so it looks like a displacement current. It's like a current that is caused by the displacements of these electrons. It's as if, right? Nothing is actually, like, electrons are not moving from one plate to one conductor to another. It's as if that's happening. Okay, so enough about transmission lines. Just know that in transmission line, you have a conductor, okay? And the signal, you can pretend as if you're a signal, let's say here, okay? You're minding your own business. You just entered this structure, which we called a microstrip line, okay? You just enter it here and you're like, okay, where am I going? Okay, tell me where to go, okay? So this is the signal. Let's say it's a voltage signal. It's going forward, right? If you design this signal, if you design this transmission line to have the impedance of 50 ohm, okay? And by that, we mean that if the signal looks at this point, right at this point, if it sees a voltage and a current that is going this way, for example, if it divides that voltage to that current, it would see a 50 ohm over this line. Okay, that's all we care about, right? So the signal is coming in. You had a signal generator that had an output of 50 ohm. Let's say you had a cable connected it to this microstrip line is 50 ohm. So signal is like, okay, I just came out of somewhere that had an impedance of 50 ohm. Now I'm entering another place that has a 50 ohm, okay? Nothing is happening. So I didn't experience any change. So I'm just going to move forward. Again, let's say the width of this trace is constant over here. Nothing is happening. It gets to this termination. Now, if this termination is anything other than 50 ohm, anything, like it's capacitive, inductive, open, short, doesn't matter, right? Now the signal is like, uh-oh, like this is not what I'm used to. Where am I going to go? Where am I going to go, right? So now depending on how much different this load is from that 50 ohm, the signal might decide, I'm going to completely go back. I'm going to just go back here, right? I'm going to just go back. There's no way I'm going to enter this, right? And when does that happen? When we have an open circuit, for example. If it's open circuit, the signal is like, I'm just gonna, there is no way, like, I have no path of going. So it's just gonna go back completely. Let's say if it's 40 ohm, right? Then in that case, I'm gonna go with another color. Oh. So let's say if it is 40 ohm, then it'll be like, okay, I guess like it's not as bad. So I'm gonna go a little bit forward, but at the same time, I didn't like it that you changed my environment. So some of me is gonna go back, right? So whenever that impedance that the signal is used to, wherever it's launched from, is different from basically what it's going through at each point, right? It can happen, this reflection, it can happen at this point when we have a Z in of the, let's say, the signal generator or the connector or whatever it is, right? To this transmission line. And this is like it has, the transmission line is shown with two conductors. It had a Z0, and then we have a ZL. That's our load, okay? So this reflection can happen right here, or it can happen right here, okay? Even if the impedance of the transmission line changes over this path, over the length, even if that happens, again, we might have reflections happening, okay? So in this straight line, we can see that the width is not changing, nothing about the circuit, this structure is changing over the length, so it's length independent, so we can show the whole transmission line with the Z0, right? So the two places that the reflection can happen is either when the signal is launched to the transmission line or when it reaches to the end of it. How much does it get reflected back, right? That depends on how different it is. So let's say this is a reflection coefficient, right? How different it is from the previous one. Right now, for example, we saw that we assume that here we had no reflections, and when we got to the end of the line, we might have had some reflections. So we can say that the reflection coefficient is ZL minus Z naught over ZL plus Z naught, right? So that is going to be our reflection coefficient. Now you can define this reflection coefficient in frequency domain or in time domain, okay? What does that mean? In time domain, okay, you basically follow the signal as it's traveling through the transmission line, and then at each moment, at each instant, you decide if there's going to be a reflection or not, okay? Now, in frequency domain, now it's a little bit different, but this thing is, this gamma can be in time domain or it can be in frequency domain. And you might know from digital signal processing or any other course you have taken that this is basically an FFT. Okay, you can take fast Fourier transform or DFT or Fourier transform to go from one of them to the other one, right? One of them might be IFFT, inverse FFT, and the other one FFT. What matters is that if ZL and Z naught are expressed in frequency domain, then you would get your gamma in frequency domain. So for example, gamma in F is ZL in F minus Z naught ZL in F plus Z naught in F, right? For example, somebody might tell you, I'm giving you a microstrip line, it is 50 ohm, right? In the band of interest, right? So you can never design a transmission line that has a constant impedance over a very wide band frequency. But let's say, for example, they say it's constant, consider it constant because it has a very wide bandwidth, right? Then in that case, you can say, okay, but my load might change with frequency. This is 50 ohm, and then I'm going to consider in the frequency of my interest that this is going to be ZL is Z naught is going to be constant. Now, when does ZL can change with frequency? You guess it right, probably. If you have a capacitor, if you have an inductor, these are all the elements, or even more complicated, right? You can have a chip or BGA or whatever you have, right? But the simplest concepts that you might be familiar with and have heard of is like capacitor and inductor. The Z of a capacitor is 1J omega C. The impedance of an inductor is J omega L, right? Simple terms, but it can complicate the reflection coefficient. Okay, so now whenever you measure an antenna, especially a narrowband one or an RF device, right? You basically look at reflection coefficient. Most of the time, you're looking at reflection coefficient in frequency domain, right? So ZL gamma in frequency domain, ZF, right, can be measured easily with what we call vector network analyzer. What you do here, basically, you have a device, right? You send a signal in, and then in different frequency, the signal is sweeping in frequency. You might say, I'm going to go from 10 megahertz to 1 gigahertz, so 1000 megahertz, right? I'm going to generate different signals with these frequencies, like a sinusoidal signal, and I'm going to see like how much of it is going to get reflected back, right? And then so VNA allows you to measure this reflection coefficient, sorry, not ZF, reflection coefficient gamma F here in frequency domain, which again, you can simply, if you know Z naught is 50 ohm, you can get ZL f from this measurement as well. It's just a simple multiplication, right? But what started this conversation, I know it's been a long one, but bear with me. Gamma in time domain, it requires another device, what we call the TDR, or time domain reflectometer. Basically allows you to measure reflection coefficient in time domain. Okay, or or the reflected signal in time domain. It might not be per se the reflection coefficient, but it shows you the reflected signal. Just like we did here. We were like, okay, we launched a signal to the line. It looked like this, right? It got to the end of it. Now, now we have some reflection back to our signal. Okay, I'm gonna explain this better. Okay, but remember, time domain reflectometer is what helps us to measure reflection coefficient or look at reflected signals in the time domain. Conceptually, it's easier because, as I said, you can imagine you're the signal, you're traveling through time, and time is a concept that is more tangible for us, right? Rather than frequency. So in TDR, what they do basically, you can have a signal generator and generate a very narrow pulse. Right? A narrow pulse, and then send this to your device, let's say. And in your device, wherever it has a connector, wherever you're interested to look at its basically the reflection coefficient, you can connect that to the TDR. The signal generator can come to the TDR as well, right? So, but the basic thing is that either TDR or a separate signal generator sends the device a very narrow pulse and looks at what's coming back, basically. For example, let's look at some conceptual questions here. This is very easy one, but at the same time, very important one. Okay, so again, we have a microstrip line here. It's a red one, and then we have a green one here, right? So the red one is going straight from a 50 ohm to a 50 ohm, and the widths and the heights and everything about this line is designed so that this transmission line have a 50 ohm Z0 as well along the line, right? On the other hand, we have this green one. Again, it's launching from 50 ohm, going to 50 ohm. And then the width, as you can see, is constant, but right here, it has a bend, okay? So what is happening here? Let's look at the impedance or the reflection coefficient that we are going to have on these lines. For example, again, the concepts are very similar. I'm going to look at the impedance of the time of the lines versus time. Okay, so let's go with the green. For the red one, it's simpler, no bend, no change along the line, right? So once you launch it from 50 ohm, it goes straight to 50 ohm, right? The signal is here, it sees 50 ohm, sees here. So as it's traveling, I'm showing a length on the line, right? But it's indicative of the time as well. It's as if the signal is going forward, right? As it's traveling through different lengths of this line, the different time is passing too. So by the time it gets, let's say this is the end of the line for us, or Tmax, we always see 50 ohm, right? Now let's look at this one. Again, the signal is starting. It's seeing 50 ohm. I'm gonna start from here again. So it's starting, going, minding its own business. 50 ohm, 50 ohm. Oops, I'm seeing a bend here. What does this bend mean? Some of you might know on a PCB, when you have a bend, that introduces some capacitance, right? Just because the width now here, the equivalent width here is a little bit wider than what you had here, right? So that increases the capacitance between this trace and the ground below it, and introduces some capacitance. Okay, so it's not, so right now Z naught at this point, it can't be 50 ohm. It's 50 ohm minus J something. Let's say C of bend. Okay. Oops. So forget about this one. So minus bend, C bend here. Okay, when you have that one, then we have an omega as well. 1 over this minus 1, basically. So the important part is that you have a 50 ohm and a minus J Z of C. Okay, the impedance of that capacitance, basically, amplitude of it. And so when this happens, what does happen to our reflection coefficient? What happens to our impedance? Our impedance is going to lose some amplitude. The capacitance, because of that minus J, is going to introduce some dip in our capacitance. Then once the signal passed the bend, again, it's going back to 50 ohm and it's getting to the 50 ohm. Okay? So if somebody tells you draw the TDR for these lines for me, or draw this impedance versus time for me, that's what you can do. For example, here, before we had a physical change on the line, like the root of the signal change, right? And you could see how it impacted our impedance, right? And imagine on a PCB in high speed, everything is about electromagnetics. Everything is a transmission line, basically. So when you're routing all of these things, you have all of these traces that come out of your IC, come out of like all the components that you have, right? All of the chips that you have to be careful that even a slight bend can cause some discontinuity in the impedance, and the impedance of the line is no longer 50 ohm. So it's going to introduce some reflections back to the signal. Here, it's a similar concept, but here, instead of changing the root of the signal, we are just changing the width of this line along the way. So I found this on Google. I thought it's a very good example here. So we have the signal launching. Again, it's starting from 0 ohm. And then as soon as it sees the line, for example, it goes to, let's say, 50 ohm, right? So if this is our standard size for 50 ohm, as soon as we have a wider width of the trace, then again, just like the bend, it introduces some capacitance, extra capacitance between the trace and the ground that is behind it. So remember the capacitance formula, it's epsilon A over D. So more area means more capacitance. D being the distance between the two plates of that capacitance. So this is A, the area, and this is D, and then in the between we have epsilon, right? So this was our regular rectangle capacitance. Then again, so as soon as we have that capacitance, our impedance is gonna go low, right? Then we are going back to our Z naught. So we're going back here to our Z naught. Then the line became too narrow. Now we have more inductive or less capacitance. So it's as if like it's an inductive, you can say, right? So when that happens, now because Z2, it's like a Z naught plus J omega L, then you can have the amplitude of Z2 is more than amplitude of Z naught, basically. Here. Then again back to Z naught. Okay, so that if you look at the impedance, getting used to like traveling as the signal, we can see how the signal sees the traces in front of it at each instant. Again, it's very easy because time is more tangible for us, and then this is basically traveling through the line. Okay. Now let's go through a more conceptual question here. Okay, we have the reflection coefficient in frequency domain, and it's given in dB. Okay, so these are negative values. Again, if you, dB is basically 20 log of gamma in value. Okay, gamma in value. And because gamma is less than 1 and more than 0, the amplitude of it, all the time, then we are going to have less than 0 dB. Okay, so we have two devices here. One of them has a reflection coefficient in frequency domain in the as a green line, and then the other one as a red line. Now, in another part, they ask us, we have also, this is the reflection coefficient, then we are interested to know the TDR, or the impedance in the time domain. And we have two lines here. Which one correspond to what in here, basically from the green and the red, right? So somebody might go to calculation mode and say, okay, I have gamma in dB. I'm going to convert it to gamma in value between 0 and 1, basically. Then I know that gamma is ZL minus Z naught, ZL plus Z naught. And if somebody gives me Z naught, since I have this gamma, then I'm going to give them ZL, right? Then the person asking question, it might be like, okay, you ran out of time. Okay, this is too much. And also you have no values here. So you have to go through looking at this conceptually. Okay, so let's do that. Let's see what's happening here. So if you look at the red line, it's almost like in DC, we have kind of like a better reflection coefficient. Oops, what's happening? Okay, for the red one, we have a better reflection coefficient than the green one in low frequencies, meaning that in low frequencies, okay, in low frequencies, we are closer to our Z naught, let's say 50 ohm, for example, okay? And I just drew this in different levels, but they are, imagine they are both like Z naught. They're starting from Z naught, okay? And then, so in low frequencies, we are sticking to the 50 ohm better, okay? Now, in higher frequencies, if you look at higher frequencies, right? Green one is basically having 0 dB reflection coefficient, meaning that the reflection coefficient, if it is 0 dB, 0 dB corresponds to 1, meaning that every part of the signal is getting reflected. And then if in dB we have a very low value here, then in the absolute value, it's close to 0, right? The lower it is in dB, the better, meaning that we have less reflections, okay? So if we are very close to 0 dB here, that means that all of our signal is getting reflected. But that's happening in high frequencies. So it means that the green line has a very high frequency disturbance along the line in the impedance, meaning very high frequency disturbance to the impedance would cause the reflection coefficient to be close to 0 dB, or basically 1 in absolute value. Now, if you look at these two lines here, which one would show you a high frequency disturbance to the line, right? So in the green one, this looks like the green one basically, because the disturbance that is happening around the impedance has a very high frequency. Whereas in this one, yes, we got away from 0 dB, but it's happening very slowly, right? So I'm gonna go, this is going to be our red line because the disturbance or the deviation from 50 ohm is happening slowly. And then for the green one, the disturbance is happening in high frequency or with a high change, and that's why in reflection coefficient in higher frequency is basically the worst. Okay, I think that's it. You can read more about TDR. There are a lot of concepts there. It's a simple concept that you might be familiar from antenna measurements, from RF devices, but in signal integrity or for basically cable measurements, it becomes very handy when you do it this way, when you just go to the time domain. And oh, what I forgot to say is that the practical application of this, besides signal integrity, is that imagine there are a lot of handheld devices, and basically you can measure TDR of a cable there, right? On that device, you can connect your cable to that TDR, and then basically, if you see reflection signal coming back based on if it is positive or negative, you can decide if this is an open cable or if you have shorted somewhere something, right? So look at these loads, Google it, or try to do this exercise of putting different terminations on the transmission line and looking at how the reflected signal would go back, because that positive or negative basically tells you the nature of this discontinuity, and it's very important. Okay, great. I hope you learned something, and yeah, let me know how you feel about this video, or if you would like to know more about these signal integrity concepts, and I try to post the stuff about it. Okay, thank you very much, and talk to you guys later.